So the fundamental theorem of calculus, right, we get to do, and it comes in two parts. And this first part is kind of, I don't know, kind of hand wavy. It feels a little awkward when we do it, when we're doing it, when we actually like use the fundamental theorem of calculus to show. But the idea behind it is so amazing. So stay with me for just the idea of it, and then just try not to get too caught up in the I do what at the end. Okay, so f of x, so our little f is continuous on a chunk of x's, and then capital X is defined to be, right, the antiderivative between a constant, right, a fixed value of x, up to a generic value of x, right, so that's what makes it a function of x, and then we change our independent variable over here, so we have this other f of t dt. So we have f of t dt, and then we're integrating from a fixed value up to x, and that generates this new function. Okay, then the derivative of that integral, so the derivative of capital F of x is equal to little f, so the inside function evaluated at x on that chunk between a and b where little f was continuous. Okay, so, or the derivative, so the rate of change, the derivative of the integral, so the big F is defined to be the integral. The rate of change of the integral, which is, right, adding up all of that area, is equal to the value of the original function at that particular value of x. So remember, area is, right, this little, in this case, it has g of x. So think of that as the area is our big F of x for the notation that I've used. So the area is equal to this function, right, this big F of x, and, right, the rate at which that area is changing, if you think about another little thin slice, right, we're adding on little chunks of height, right, and that's equal to that little lamina, right, of area that gets added in, right, and the rate at which the area changes is equal to the function value there. Oh my gosh, that is so fun. Okay, so in practice, so this is the part where you just kind of got to roll with it. When we do this, so we're thinking about this definition, the lower limit is the constant, the upper limit is the x, okay? If it's different, then we're going to have to use some of our integration rules and maybe a substitution chain rule thing to figure it out. Okay, so the first one, so capital F, our area function is defined to be, right, the integral from 3 to x of t cubed dt, and we want the rate at which that's changing. So we want f prime. So f prime of x, all we do is we replace the variable with an x. So that equals x cubed. And for this one, you could actually do it. You could find the antiderivative and then differentiate it, and you could see that this is what it is. Okay. When I look at the next one, notice I've swapped them just so we can practice. So I have the x on the bottom. So to flip the limits of integration, remember we can swap the limits, but it involves a negative sign. So this is equal to negative integral pi to x of sine of t dt. And so if I take the derivative of this, right, the derivative of the integral, as long as the x is on top, we just get that same function back with the new variable in. Okay. No plus c's if you're thinking, well, where's the plus c on this? So remember, we're finding the derivative. This is capital F prime of x is equal to that. We take the derivative, that constant that came in when we did our antiderivative, the derivative of the constant is 0. We don't have it anymore. Okay, so this next one, oh, shucks, I've got variables on both sides. What am I going to do? Well, what I'm going to do is I'm going to pick an arbitrary value, right, someplace in the middle, and it doesn't matter, right, and e to the t is, right, defined over all real numbers, so I'll just write a nice one. How about 0? So I'm going to have to redefine my f of x. I'm going to have to go from 2 times x to 0 of e to the t dt, and then I would add that then from 0 to 6x of e to the t dt. Okay, so that first one, notice your x is in the bottom, but I need it to be in the top, so we're going to go ahead and swap those guys with your negative sign. So now I've got negative integral 0 to 2x e to the t dt plus 0 to 6x. I don't write the zero constants on the bottom. That's up top. That's good. E to the t dt oh, sorry. Okay. So then, but now it's not just x. Yikes. So that means when I go to substitute it, right? When I go to do my chain rule, if we think about what that would be, right? I'm going to get an extra times the derivative of what that top is. So think about your chain rule. So I'm going to get negative e to the 2x times 2 plus e to the 6x times 6, right? Or 6 e to the 6x minus 2 e to the 2x. Those guys, I can't tidy those up any more than that.